Hello everyone, in today's lecture I'm going to explain how we can use continuous time Fourier series and discrete time Fourier series to find the output of LTI systems. Previously you saw that signals in the format of e to the st are eigenfunctions of LTI systems. That means if we apply the input signal e to the st to an LTI system, the output is going to be the scaled version of the input signal. In this exponential, s is a complex number, which we can represent as alpha plus j omega. And h of s, we defined it as using this integral. H of s was equal to integral of h of tau e to the minus s tau d tau. And h of s is in general a complex number. And we found this expression or this integral for h of s using the convolution integral, which is defined for LTI systems. We used y of t equal to x of t convolved with h of t, and then from there applied x of t equals to e to the st, and then we ended up with y of t being equal to e to the st multiplied by some expression, that integral, which didn't depend on t, so we named that integral as h of s, that expression as h of s, and we call it the transfer function of the LTI system. So far, we know that if we apply e to the st to an LTI system, the output is going to be equal to h of s multiplied by e to the st. Okay, so these base functions, e to the st, I provided a few examples of them just for you to see how they look like. So s is a complex number in general, alpha plus j omega. These are complex exponentials that are different for every complex s value. Regardless, if you apply each one of them to an LTI system, the output is going to look similar to the input signal. It's just that it's going to be multiplied by a constant, by a complex number. So if you apply e to the alpha 1 plus j omega 1 t to an LTI system, the output is going to be equal to e to the alpha 1 plus j omega 1 multiplied by t. This whole thing is going to be multiplied by this expression, which is related to impulse response, or h of t of LTI system. All right, so now let's limit ourselves to a subset of eigenfunctions e to the st in which s is purely imaginary. So I'm going to set the real, if s equals to alpha plus j omega, let's set alpha equal to 0 and then use only the exponentials in which s is equal to j times k omega naught. So the set of base functions that you had is reduced to e to the 0, e to the j omega naught t, e to the j 1 times omega naught t, e to the j minus 1 times omega naught t, j 2 times omega naught t, and so on and so forth. So these purely imaginary numbers are all related to each other by a factor of k. All right, so now we are applying each one of them to an LTI system, similar to the previous case. I'm going to get the same exponential at the output, and that exponential is going to be scaled by a complex number, which depends on the impulse response of our LTI system. Okay, so now let's look at the Fourier series representation of periodic signal with period of t that have finite energy in one period. So we had the synthesis equation before, and I'm going to write the components of this one. And as you can see, x of t has several of these complex exponentials, and I know the response. I know how I can calculate the response of the system, LTI system, to each one of these complex exponentials. So if you apply e to the minus j omega naught t, multiply by a number, by scalar factor a to the negative, by a complex value a negative 1 here, the output is going to be equal to I had a negative 1 in here. So a negative 1 e to the j omega naught minus j omega naught t multiplied by this complex number here, h of minus j omega naught t. The second one, if you apply the second one, this part is going to show up at the output without any change. The whole thing is going to be multiplied by this factor. All right, and so on and so forth. So if in general any ak e to the jk omega naught that's applied to the system is going to result in ak e to the jk omega naught t multiplied by h of jk omega naught. In h of jk omega naught is the fundamental frequency of the input signal, the periodic signal. K is this term that I have. This shows the case component of the x of t, and h of j omega is the frequency response of the system, or h of s when s is equal to j omega. All right, so if you apply x of t, the general format of x of t, y of t is going to look similar to x of t. It's going to consist of a summation of terms in which you have ak to the jk omega naught t multiplied by h of jk omega naught. So the Fourier series representation of a continuous time signal will tell us which frequency components, by that I mean the k times omega naught terms in the exponential e to the jk omega naught, are present in the given signal in x of t. So if I write the Fourier series representation, I'm going to see which ak components are there, and that's going to tell me which frequency components exist in my x of t. Now, and the Fourier series coefficients of any continuous time signal are going to tell us the strengths of each frequency component in the given input signal. H of j omega evaluated at omega equals to k times omega naught, on the other hand, is going to tell us the behavior of LTI system at the k times omega naught frequency value that we are looking for. So k times omega naught is one of the frequency components in the case frequency component in the x of t. Okay, so now let's see how we can use a continuous time Fourier series to solve LTI systems. Previously, you saw how to find the Fourier series coefficient of a continuous time periodic signal. Now we are going to solve an example, and through that example, see how we can find the output for the given continuous time periodic signal using CTFS. All right, so the example is consider an LTI system with impulse response h of t is delta of t minus 1. This is an LTI system. That means if we have the impulse response, we know everything about the system. And use the continuous time Fourier series to find the output of the system to input signal x of t is 1 plus 2 cosine 2 pi t minus sine of 3 pi t. So I first need to find out which frequency components exist in x of t with what strengths and how my system, LTI system, behaves at each one of these frequency components. Okay, here are the steps. Step 1, we will find AK coefficients of x of t. Step 2, we will find the frequency response of the LTI system. In other words, we will find h of j omega. Step 3, we will find the output using this expression, because I know for every e to the jk omega naught t applied to the system, the output is going to be the scaled version of that one, and I know I can write x of t as a linear combination of these e to the jk omega naught t terms. All right. Step 4, since x of t is a periodic signal with period of t and fundamental frequency of 2 pi over t, the output of system, y of t, is also going to be periodic with period of t. With that, now that I know y of t is periodic with period of t, I can use Fourier series representation or synthesis equation to express y of t as a combination of its frequency components. This time I'm going to use bk to represent the Fourier coefficients of y of t, and then you have this expression here for y of t. If you compare these two together, you can find the Fourier coefficients of you can find the Fourier series coefficients of the output as a function of Fourier series coefficient of the input signal. So they are related to each other. So the first one in here comes from knowing that my output is periodic with period of t, and the second one in the second equation comes from knowing how LTI system behave when you apply complex exponentials in the format of e to the jk omega naught t as their input. All right, so now let's apply all of these steps to find the output of the system to this input signal. So I wrote x of t as a summation of x1 plus x2 plus x3, and I drew them to show you the frequency of each one of them. They're simple signals, cosine function. The first one is DC, second one is cosine 2 pi t, and the third one is cosine of 3 pi t. So this is, and the third one, and the fourth one is x of t. Okay. I want to find the Fourier coefficients of x of t, and x of t is given in the sinusoidal format. So the preferred approach for finding AK is to write or to express x of t in terms of complex exponentials and then compare those terms with the components of the synthesis equation and then extract the AK values. So let's do that. I use Euler formula to write cosine functions in terms of complex exponentials, and so instead of 1, I wrote 1 multiplied by e to the j multiplied by 0, and so on. And if you continue simplification, you're going to see that x of t can be represented in terms of complex exponentials, and I'm ready to compare them with the synthesis equation to extract AK values. All right, I compare them, and these are the AK coefficients for the given x of t. I have two cosine functions, so I'm going to get 2 AK values for each one of them. So I'm going to have 4 AK values just because I have cosine of 2 pi t and cosine of 3 pi t. And then I'm going to have one DC. I have one DC value there, 1. So I'm going to have a 0 as well, a non-zero value for a sub 0 as well. So altogether, I expect to get 5 AK values, and then I calculated 5 AK values. All right. Now that we're done with analyzing finding AK values and figuring out which frequency components exist in x of t, let's move on and look at our system. We want to find the frequency response of this system, and that can be calculated by using the equation that relates h of j omega to h of t and knowing the equation of h of t. The impulse response of the system is given. It's h of t equals to delta of t minus 1. And then I'm going to use the integral that I found to define h of j omega and find the h of j omega using the given h of t. All right, so this integral is what we found when we defined the transfer function, or h of s, and so substituted s with j omega. And then I'm ready to evaluate this one. So what I'm going to do is to find h of tau, which is going to be equal to delta of tau minus 1. So I'm going to replace this in here and then evaluate this integral. So at this point, I'm ready to use the sampling property of delta function. If you remember, delta of tau minus 1 e to the minus j omega tau is equal to delta of tau minus 1 multiplied by e to the minus j omega multiplied by 1, because delta of tau minus 1 is 0 everywhere other than tau equal to 1. So I can replace this one with delta of tau minus 1 multiplied by e to the minus j omega. I replace tau with 1. All right, so if you do that, you're going to have e to the minus j omega in your integral, which doesn't depend on tau, and you're running this integral for tau values. So e to the minus j omega can get out of the integral. I'm going to take e to the minus j omega out of integral, and then it's going to look like this. And integral of delta of tau minus 1 d tau for all tau values is equal to 1. You saw that in the previous lectures. So with that, h of j omega is equal to e to the minus j omega. Okay, so h of j omega, or the frequency response of an LTI system, tells you the behavior of the system for every frequency component that you might have in your XFT. It tells us the behavior of the system in the frequency domain. All right, so this function is a complex function, that complex valued function. That means I can find the magnitude and phase of this function for every frequency value. And if you do that, you're going to see that the magnitude of h of j omega is equal to 1, and the phase has a linear relationship with omega. All right, so which tells me that this system is not going to affect the magnitude of the frequency components of that might exist in any given x of t that's applied to the system, but it's going to manipulate its shift. It's going to its phase. So it's going to change the phase values in the frequency component of input signal. Let's see how it happens for our given x of t. So I have an expression for calculating y of t. It's given in here. And I know that x of t is periodic, so y of t is also going to be periodic with the same period. I have the AK coefficients for x of t, and I found h of j omega. And x of t had a fundamental frequency of omega naught equals to pi. So I want to find h of j omega at k times omega naught points, or k times pi frequency value. So I'm evaluating h of j omega at k times pi points. All right, so let's go ahead and look at that one. So again, I use the expression that I found for y of t. Because I had h of j omega in here, instead of omega, I wrote k times omega, and I found h of jk omega. All right, with that, I have y of t equals to summation of ak multiplied by e to the minus jk pi multiplied by e to the jk pi t. Right. If you plug in every k value, non-zero k value in this expression, you're going to have this expression for a y of t. You had 5 non-zero ak values, so your summation is going to be reduced. This infinite sum is going to be reduced to 5 non-zero components. All right. Okay, so I'm going to ask you to pause the video and follow on my derivations or simplifications for finding y of t. I use Euler formula to simplify the expression of y of t from complex exponential format to a sinusoidal format that I have in here. So pause the video and redo these calculations and compare them with the given ones. All right, so ultimately y of t is equal to 1 plus 2 times cosine of 2 pi t minus cosine of 3 pi t minus pi. So as you can see, the system did not affect the amplitude of each one of these frequency components. It just added some phase shift to the third component, cosine of 3 pi t is changed to cosine of 3 pi t minus pi. The graph of x of t and the graph of y of t are provided here. Now let's look at how we can use DTFS to find the output of discrete time LTI systems to input signals that are periodic with a period of n. So here's an example. Consider a discrete time LTI system with input signal with impulse response h of n, and assume that a periodic input signal x of n with period of n and fundamental frequency of 2 pi over n is applied to the system. Find the output of the system, or y of n. The steps are similar to the steps that you took for finding the output of continuous time LTI systems to given periodic and continuous time signals. So these are the same steps, and more or less the process is similar. There are some differences, and one of them is that x of n, the synthesis equation for x of n is different from the one that you had for a continuous time case. And here I want to, for discrete time systems, you want to find h of e to the j omega, which is the frequency response of your system compared to h of j omega. And then y of n is going to be calculated with this expression, which is this in which the summation has a finite length, so you're summing it for only n values of k. All right, so again, because x of n is periodic with period of n, y of n is also going to be periodic with period of n. All right, so because y of n is periodic with period of n, I can write this expression, which is the synthesis equation for y of n. And because my x of n can be written using the synthesis equation, can be written as summation of these specific complex exponentials, e to the jk omega naught n. The output of the system is going to be scale version of these complex exponentials. And then I can write y of n as summation of ak to the jk omega naught n multiplied by h of jk omega naught, which is the response of the system at k times omega naught points. So if you compare these two equations, you can find the relationship between bk and ak. Ak are Fourier coefficients of input signal, and bk are the Fourier coefficients of the output signal. And h of e to the jk omega naught is the frequency response of this LTI system evaluated at k times omega naught points. All right, let's take a look at an example. The frequency response of an LTI system is given. In this example, some of those steps have already been accounted for. For example, the Fourier series coefficients of x of t is given to you, so you don't need to find them here for this example. So you can skip step 1 of the whole entire process. So I have AK values and I have the frequency response. So I don't need to find the frequency response using the impulse response of the system. H of j omega is given to you. So I need to find h of j omega at every frequency component that is present in my x of n. With that, I need to find the frequency, the fundamental frequency of x of n, and then move on, evaluate h of j omega at k times omega naught point. All right, so n equals to 3. With that, omega naught is going to be equal to 2 pi over 3. All right, so I have 3 non-zero AK coefficients, so I expect to get at most 3 non-zero BK coefficients. And I know that y of n, because x of n is periodic with period of 3, y of n is also going to be periodic with period of 3. It's just that BK coefficients are equal to AK coefficients multiplied by a parameter that's related to h of j omega. So if h of j k omega naught is equal to 0 for any of these k parameters, BK is going to be equal to 0, even though AK is not 0. All right, so at this point, I know that I expect to get at most 3 non-zero BK values. All right, so using the equation that relates BK to AK, I have BK is equal to AK multiplied by h of e to the j k omega naught, which is equal to ak multiplied by h of e to the j k 2 pi over 3, right? So for a sub 0, that means for k equals to 0, I have b sub 0 equals to a sub 0 multiplied by, I write this when I want to evaluate h of jk omega naught for any k value, I like to write it this way because it's less confusing to find the value of h of jk omega naught, h of e to the jk omega naught. So I'm going to write it e to the jk omega naught evaluated at k times omega naught equals to 0 multiplied by 2 pi over 3. All right. So with that, I have that I'm going to write it as a0 multiplied by h of e to the j omega evaluated at omega equals to 0. Right. So I know the value of a sub 0, it's 1. I want to find the value of h of e to the j omega at omega equal to 0. From this expression, I can see that for omega equals to 0, the value of h of e to the j omega is 1. So it's going to be equal to 1, and that's going to be equal to 1. So b sub 0 is equal to 1. Let's find out the value of bk for k equal to 1 and negative 1. For k equals to 1, b sub 1 is equal to a sub 1 multiplied by h of e to the j k times omega naught, evaluated at k times omega naught equals to 1 multiplied by 2 pi over 3, which I can write it as a1 multiplied by h of e to the j omega for omega equals to 2 pi over 3. So I'm coming here, I have the equation of h of j omega, and omega equals to 2 pi over 3 is here. 2 pi over 3 is less than pi and greater than pi over 8. So for that omega value, h of e to the j omega is equal to 0. As a result, I have j multiplied by 0, which is equal to 0. So b1 is equal to 0. Looking at k equal to negative 1, b negative 1 is equal to a negative 1, h of e to the j omega for omega equals to k times omega naught, which is equal to negative 1 multiplied by 2 pi over 3. So I'm finding it for omega equals to negative 2 pi over 3. All right, with that, a negative 1 is negative j multiplied by value of h of e to the j omega at omega equal to negative 2 pi. Again, omega is in this range. As a result, the value is 0, so I'm multiplying it by 0. That's going to be equal to 0. b sub 0 is going to be, I calculated b sub 0 as 1, and b1 was equal to 0, b2, 1, b negative 1 was equal to 0 as well. With that, I can write y of n. Y of n is equal to, I can use the synthesis equation because I only have one non-zero bk coefficient. So I'm going to use the synthesis equation. Sigma bk e to the jk omega naught n. I need to run this summation over one period. So I'm going to do it for k equal to negative 1 to 1. Because n is equal to 0, because the period of input signal is 3, the period of output signal is going to be equal to 3, and I only need 3.3 components in this summation. Negative k equal to negative 1, k equal to 0, k equal to 1, 3 components. All right, so that's going to be equal to b sub 0 multiplied by e to the j multiplied by 0. That's going to be b0. This is equal to 1. So y of n is equal to 1 for all n. This is the DC term, right? There's no variation in y of n. I can draw y of n, and that's going to be equal to 1 for all n values. All right. Thank you for watching.